Hi, everyone. My name is Orr, and I'll talk about a theory of unsupervised translation for understanding animal communication. This is a joint work with David Gruber, Shafi Goldwasser, and Adam Talman-Kalai. So before we translate animals, let's think about human translation. Okay, so I have here a very simplified, stylized translation challenge. On the left, we have sentences in Welsh, and on the right, we have sentences in English. I don't speak Welsh, but I do speak English, and my goal is to translate the sentences on the left to the sentences on the right. I encourage you to pause the video now and try to think about how you would do that. All right, well, whether you pause the video or not, I'll show you an approach to a solution. And this will give us some intuition that will inform our theory down the line. Okay, so first off, we see that on the right, we have sentences in English. They talk about some fish eating some other fish. Sharks eat salmon eat herring, and so on. And also, the sun is warm, which seems like an outlier and unrelated. Well, we see that the word eat appears in all the sentences on the right, all the relevant ones. So we'll assume that it's the same word that appears in all the sentences on the left. And then we can uncover that sharks are the only fish that eat themselves in this collection of sentences. And so we can uncover this connection here. And more generally, we can read the sentences on the right and think of some kind of knowledge graph of which fish eats which other fish. This is what this graph would look like. We can trace it out and uncover the meaning of the remaining words. All right. So you can pause the video again and think of some takeaways from this solution that I just showed you, but let me tell you my takeaways. So some anecdotal observations are having a prior is useful. Okay. Having a prior about what the text on the left might talk about is useful. In this case, our prior was that knowledge graph that we know that most of these sentences talk about fish eating other fish. Another one is we shouldn't confound key concepts. Okay, so what do I mean by a key concept? I mean that shark and salmon are obviously very different in these collections of sentences because, for example, sharks eat themselves, but salmon don't. But on the other hand, if I had chosen the word consume instead of eat, I wouldn't call that a key concept that's being confounded. That seems more of a lighter, less important difference. Another obvious observation is that longer text helps. So if we just had a collection of very short one-word sentences, then we wouldn't be able to draw any relationship between any two words. And lastly, there is some sort of underlying computational puzzle that we solved to find out which fish corresponds to which fish according to our knowledge graph. All right, so this talk is about an information theoretic framework for unsupervised translation, abbreviated UT. And the question we're set out to answer is, what are some sufficient conditions for UT to work, at least in theory? Right, so the outline for the rest of this talk is I'll give you some motivation where this question is coming from. I'll define what is unsupervised translation. I will show you our analysis of when might it work. And if time permits, I'll mention a model of language that satisfies that for which our analysis actually holds. And we'll conclude. All right, so the motivation of this project, it's one of my favorite parts about this project, is the Cetacean Translation Initiative, SETI, which aims to understand sperm whale communication. This initiative has many incredible scientists of all disciplines, linguistics, computer science, robotics, of course, marine biology, coming together and trying to harness modern computational and robotic tools to tackle this huge problem, very interesting problem of translating sperm whale communication. All right, so I highly encourage you to look them up, Project SETI. There is a paper out there detailing their whole end-to-end approach of translation. And I'll just note that this project is really just a tiny sliver in this initiative. We just tried to do some math and find some theory that would help inform some of the challenges in translating sperm whale communication. All right, so before I talk about unsupervised translation, let's talk about supervised translation. All right, so The goal in supervised translation is to learn a translator from some source language X to some target language Y, right? And in supervised translation, importantly, we have labeled samples, okay? What I mean by that is we have a sentence on the left, j'adore le calamar, and the corresponding translation of the sentence in English on the right, I love squid. So you can imagine that there is this Rosetta Stone that has the translation of just a few sentences, and maybe we can use the knowledge encoded in that Rosetta Stone to come up with a general translation, right? So in this work, just for simplicity, we'll assume that there is a ground truth translator, okay, a function. It's even we're gonna assume that it's one-to-one, translating any sentence from the source to the target. You'll see that we end up with a pretty rich theory even under this assumption. And of course, as I said, formally, the goal is given M labeled samples. So F star is our ground truth translation, XI and F star XI. Our goal is to learn a translator F theta from X to Y. Theta you can think of as the parameters of the model, so maybe the parameters of the neural network. And of course, we measure the error. So let me say something about that in a moment. So first off, I just want to say, to us, a language is a distribution over sentences, right? So you can think of all imaginable French sentences. And then the French language, what we are collecting samples from, are sentences weighted according to, the probability that they're actually uttered. So they actually appear in our training data. So mu x is the likelihood of hearing sentence X in the source language. And then the small error that we're trying to minimize is a sum loss function that measures dissimilarity between sentences in the target language, right? Well, what about whales? Sperm whale communication sounds something like this. Okay, so what you just heard is that these sequences of clicks, okay, they're called codas. And you can think that each coda can be digitized to form kind of like words in sentences like this. So this is entirely outside the scope of our work, how to digitize codas. So for us, we'll just assume that we have a collection of codas. 3R is one coda. It means that there's 3 clicks in a regular interval space, or regularly spaced interval, sorry, and 6I and 2R and so on. But of course, the problem is that although we do have a small collection of sentences formed by codas, we have no labeled samples. There is no Rosetta Stone that translates just a few whale communications into English. In other words, there is no bilingual mermaid that speaks both whale and English and can label a few whale communications for us. We really have nothing to work with here. All right, so this is our setting here. More generally, this is the unsupervised translation setting. So in the unsupervised translation setting, what we have is a collection of sentences in the source language and a collection of sentences in the target language, but they're completely unaligned. They might be talking about different things altogether. All right, so we're still going to assume the existence of a ground truth translator F star. And now the goal is, given unlabeled samples, X1, X2, and so on, Y1 and Y2, the goal is to learn a translator with small error. Just a few more notes about our model. Note that we can't actually observe the loss here because we have no access to the ground truth translator F star. But still, you can imagine that there is some kind of loss that is to be minimized. So another fairly minor assumption is the realizability assumption. We'll assume that F star is expressible by our hypothesis class. So there is an instantiation of the neural network that is a good translator, right? Obviously, if there isn't one, we'll never be able to use the hypothesis class to learn a good translator. And lastly, I'll note briefly that we assume access not just to sentences in the target language, but actually to a language model that approximates the distribution of the target language. I'll say much more about that in a moment. All right, but before we continue, let me just briefly mention some existing work on unsupervised translation. So there really has been a boom in the past few years in attempts to make unsupervised translation work. And it does indeed work in some settings. So what you have here is some of the work in 2018 and 2019. You can see that it does translate French to English fairly well, but of course, French and English are syntactically somewhat similar, and also the corpora used for training was very similar. So it is a different setting than ours, but at least empirically, unsupervised translation is possible in some settings. And we're trying to find out when might unsupervised translation work. So in the rest of the talk, or at least for the next while, I'll show you two conditions that we identify in our framework for unsupervised translation that allow UT to work. And then I'll try to show you a model in which these conditions are satisfied, right? So when might unsupervised translation work? So the first condition is we assume that there is access to a statistically good prior. What is a statistically good prior? So a prior answers the question, if whales communicated in English instead of with clicks, what would they say? What do I mean by that? So here we have our source language and our target language. These are distributions over strings with entirely different alphabets, right? But you can imagine that you take the ground truth translator, F star, and you translate all of the sentences in the source language into the target language alphabet, right? This gives you some kind of odd language that we call the translated language. It's an entirely hypothetical language. No one speaks this language, but what a prior gives us is an approximation to this translated language, or to this translated language distribution. All right, so a good prior row, it's a prior over sentences in English. It approximates this F star composed with mu, this translated language. All right, more formally, we say approximation, we measure the goodness of the prior with the cross entropy. So that's defined as you sample a sentence. Let me not read this out loud. You can pause this and definitely stop by if this is still unclear. And it's parameterized by some parameter eta. All right, but yeah, let me say intuitively, row of y is an English sentence. Row of y estimates how plausible it is that y was a translation from the source language, from Walish. All right. And we have an idea of how we might obtain good priors using existing pre-trained language models such as GPT-3. And I'll try to say something about that later in this talk. The second condition we call no plausible confoundings. It's similar but different than the good prior, right? So a translator, F theta, any translator might confound certain words or concepts. So for example, it might confound north and south, or Sarah and Mary. In this case, we might not be that bothered by these confoundings because maybe whales never say the word Sarah or Mary. So it doesn't really matter if our translator swaps Sarah and Mary. The case of North and South is slightly more delicate. North and South certainly do matter, but without observing the whales swimming, through the ocean and so on, we might never be able to tell whether the sentence "tomorrow we swim north" or "tomorrow we swim south" without observing where they actually swam the next day. On the other hand, there are different kinds of confoundings. For example, swapping bicycle and attack. So this is a really bad confounding for a translator to make, and that's because whales probably talk about attacking. Sperm whales are predators, but they probably never talk about bicycles. So this is a bad swap to make. And similarly, orca and squid are really bad words to swap, and that's because whales eat squid, but whales are attacked by orcas. So these really should not be swapped by a translator. So that's kind of what I just said. North and South, it's not great, but we might tolerate these kinds of swaps. On the other hand, swapping orca and squid certainly shouldn't work out because whales eat squid, but orcas eat whales. So more formally, we say that a prior row and a translator family f theta have no plausible confoundings. And this is parameterized by p and epsilon. If for any theta, for any translator that has high loss or high expected loss, our prior is able to rule out words from is able to rule out translations from this translator with some probability. So this is not very high probability. It's just greater than epsilon. Yeah. So really what condition two is saying is that if we have a translator that confounds important concepts, then our prior should be able to rule out translations from this translator. And the reason we think this might be true is, as I just said, if you have a sperm whale saying the sentence, allegedly saying the sentence, today I ate some squid, then if squid is swapped with orca, you'd have the sentence, today I ate some orca. And as we'll show in a bit, we think that a good prior, even GPT-3 would be able to know that sperm whales are more likely to eat squid than orca. All right, so with these conditions in hand, what does our main theorem show? It basically shows that if the conditions are met, then unsupervised translation is possible. But what do I mean by that? I mean, we come up with this algorithm. It's a fairly simple and very inefficient algorithm that we call unfishy. This algorithm takes as input samples from the source language, access to the prior row, as well as the parameter, some parameter bound p, and of course, access to the translator class theta, and it outputs a translator f theta hat. And what our theorem shows is that with high probability, the translator learned by unfishy has small error if it's given sufficient samples. All right, so these are the parameters here. You can pause the video and take a look at the parameters if you'd like. I just want to note two things about this. One is that this algorithm is highly inefficient, so it basically loops through all possible translators, which is very, very prohibitive computationally. And second of all, that the sample complexity M here is comparable to the sample complexity you get in supervised learning or supervised translation, specifically using an Occam's razor style bound. So you can kind of conclude that if the conditions are met, then there is some loss in the sample complexity, but it's not too different than the supervised setting, which some might find surprising. All right, so with the time I have left, I don't think I'll talk about the random subtree language model, but please stop by during the live session or reach out if you'd like to talk about it. I'll flash through these slides. I'm sorry about that. What I do want to say is how we might get a good prior from language models. All right, so I'll just use GPT-3, OpenAI's GPT-3 language model. It's a language model for us is something that can generate sentences, or just as we did previously, assign sentences with probability. That's what we really need. All right, so just as a show of force, language models, GPT-3 knows quite a lot about sperm whales. So for example, here we prompted GPT-3 with \sections, sperm whale sleeping patterns. We're like, please write a paper for me about sperm whale sleeping patterns. And this is what GPT-3 came up with. It noted that sperm whales are one of the few species of mammals that exhibit unihemispheric sleep and so on. This is way more knowledge of sperm whales than your average person on the street, I'm willing to bet. So really, we know that models that like pre-trained good language models know something about sperm whales. How can we access this knowledge? So this is the idea. How can we get a prior from a language model using prompting, right? So if we ask GPT-3, tell me which sentence is more likely. I just ate a giant squid, or I just ate a giant cheeseburger. GPT-3 will say the latter sentence is more likely. And I agree. If you ask an average person, they're probably more likely to eat a giant cheeseburger than a giant squid. But If you prompt GPT-3 with a sperm whale said, I just ate a giant squid versus a sperm whale said, I just ate a giant cheeseburger, then GPT-3 will correctly say the first sentence is much more likely, right? So basically, the idea behind prompting is to add a prompt before the sentence that you're trying to query the prior with, add a prompt that hones the prior into the relevant domain. So in this case, we wrote a sperm whale set. All right. So this was pretty simple and hand wavy. That's the general idea. We're out of time, so let me conclude and talk about some future work. So in conclusion, we show an information theoretic framework of unsupervised translation, and we identify some conditions that make unsupervised translation possible in theory, right? With an inefficient algorithm, but an algorithm nonetheless. We also show, but I didn't really have time to talk about it, a simple probabilistic model that satisfies these conditions, just so that they're not just floating there in the air. And lastly, some future work. So we'd love to generalize our work to lossy translators. That's translators or ground truth. The case when the ground truth is not a one-to-one nice function, just as we assumed in our work. We think it's really important to generalize this work to the computational setting. As I said many times over, the theorem that we have gives us an inefficient translator. So in a sense, it's an information theoretic guarantee, but it doesn't really tell us what we can do in practice. And lastly, we probably want to compare this theory to existing empirical evaluations. So there has been some prior work on unsupervised translation, empirical evaluations, taking known unsupervised translation models and comparing them to supervised translations. We can't do that yet because our whole theorem and all of our guarantees are information theoretic. But if we made them computational, we could see how these line up with the existing empirical evaluations and maybe learn something new. So that's it. Thank you very much. I'm looking forward to meeting all of you in the virtual session. Please reach out if you have any questions. And thanks again.